Hello, everyone. Welcome to part 3 of this series. This screencast will be the first of 2 or 3 on neural IR, and in it, we'll be exploring the inputs, outputs, training, and inference in the context of neural IR. Let's quickly start with a reminder of our setup from the previous screencast. Offline, we're given a large corpus of text documents. We will pre-process and index this corpus for fast retrieval. Online, we're given a query that we want to answer. Our output will be a list of the top K most relevant documents for this query. In the classical IR screencast, we discussed BM25 as a strong term matching retrieval model. So should we just use BM25? The short answer is that we could. But if our interest is getting the highest quality that we can, then we should probably be using neural IR. As we will see, neural IR makes a lot of use of our NLU work in creative and interesting ways. The long answer to whether we should be using BM25 is that it depends. Among other factors, it depends on our budget. Each IR model poses a different efficiency-effectiveness trade-off. In many cases, we're interested in maximizing effectiveness, maximizing quality, as long as efficiency is acceptable. Let's begin to explore this on the MS Marco collection that we introduced in the previous screencast. Here, we'll be measuring effectiveness using the mean reciprocal rank at cutoff 10. And we will measure efficiency, and in particular latency, using milliseconds. This figure here shows BM25 retrieval using a popular toolkit called Ansarini as one data point within a wide range of MRR values and latency possibilities. Just as a reminder, lower latency is better. And the latency here is shown on a logarithmic scale. And higher MRR is also better. The higher our MRR is, the better the model's quality. So what else could exist in this large empty space for now? We're going to see this space fill up with many different neural IR models over the next couple of screencasts. And the central question now and then will generally be, how can we improve our MRR at 10 or whatever effectiveness metric we choose to work with, possibly at the expense of increasing latency a bit? Okay, so let's actually take a look at how neural IR models will work, specifically at their input and output behavior. For the purposes of this short screencast, we'll treat the neural ranker as a black box. We will consider various implementations for this black box function in the next screencast. We will feed this neural IR black box a query and a document, and the model will do its thing and return to us a single score that estimates the relevance of this query to that document. For the same query, we will repeat this process for every document that we want to score, and we will finally sort all of these documents by decreasing relevance score. And that will give us the top K list of results. So far, this sounds simple enough. But how should we train this neural model for ranking? This might not be super obvious, but one pretty effective choice is simply two-way classification, pairwise classification. Here, each training example will be a triple. Specifically, each training instance will contain a query, a relevant or positive document, and an irrelevant document or a negative. In the forward pass during training, we'll feed the model the query and the positive document. And separately, we'll feed the query and the negative document to the neural ranker. And we'll optimize the entire neural network end-to-end with gradient descent using simple classification loss. In this case, cross-entropy loss with softmax. The goal here is to maximize the score of the positive document and to minimize the score assigned to the negative document. Recall that we can get positives for each query from our relevance assessments, and that every document that was not labeled as positive can often be treated as an implicit negative. So we could use this in generating triples for two-way classification training for our neural ranker. Once our neural ranker is trained, inference, or actually conducting the ranking, is very easy. Given a query, we'll just pick each document, pass the query and the document through the neural network, get a score, and then we'll sort all of the documents by score. And this will give us the top K list of documents. However, there is just a small yet very major problem. Collections often have many millions, if not billions, of documents. Even if our model is so fast that it processes each document in 1 microsecond, 1/1,000,000th of a second, it would still require 9 seconds per query for a data set like MS Marco with 9 million messages, which is way too slow for most practical applications. To deal with this in practice, neural IR models are often used as re-rankers, models that rescore only the top K documents obtained by another model to improve the final ranking. One of the most common pipeline designs is to re-rank the top 1,000 documents obtained by BM25. This can be great because it cuts down the work for a collection with 10 million passages by a factor of 10,000, because we only need to rank 1,000 documents with the neural model. But it also introduces an artificial ceiling on recall. It limits recall in an artificial way, since now all of the relevant documents that BM25, our first stage ranker, fails to retrieve cannot possibly be re-ranked highly by our shiny new IR ranker. So can we do better? It turns out that the answer is yes. We'll discuss the notion of end-to-end retrieval later, where our neural model will be able to quickly conduct the search by itself over the entire collection without a re-ranking pipeline. But first, we'll discuss a number of neural re-rankers in detail in the next screencast.